In mathematics, a multiplicative calculus is a system with two multiplicative operators, called a multiplicative derivative and a multiplicative integral, which are inversely related in a manner analogous to the inverse relationship between the derivative and integral in the classical calculus of Newton and Leibniz. The multiplicative calculi provide alternatives to the classical calculus, which has an additive derivative and an additive integral. There are infinitely many non-Newtonian multiplicative calculi, including the geometric calculus and the bigeometric calculus discussed below. These calculi all have a derivative and/or integral that is not a linear operator. The geometric calculus is useful in image analysis. The bigeometric calculus is useful in some applications of fractals. Multiplicative derivatives. Geometric calculus. The classical derivative is f single quote x equals lim h 0 f x plus h minus f x h. Display style f x equals lim underscore h to 0 f x plus h f x over h. The geometric derivative is f x equals lim h 0 f x plus h f x 1 h. Display style f caret asterisk x equals lim underscore h to 0 left f x plus h over f x right caret 1 over h. For the geometric derivative, it is assumed that all values of f are positive numbers. This simplifies to f x equals e f single quote x f x. Display style f caret asterisk x equals e caret f x over f x closing curly bracket. For functions where the statement is meaningful, notice that the exponent in the preceding expression represents the well-known logarithmic derivative. In the geometric calculus, the exponential functions are the functions having a constant derivative. Furthermore, just as the arithmetic average of functions is the natural average in the classical calculus, the well-known geometric average is the natural average in the geometric calculus. The geometric calculus. A similar definition to the geometric derivative is the bigeometric derivative. f x equals lim h 0 f 1 plus h x f x 1 h equals lim k 1 f k x f x 1 lane k. Display style f caret asterisk x equals lim underscore h to 0 left f 1 plus h x over f x right caret 1 over h equals lim underscore k to 1 left f kx over f x right caret 1 over lane k. Closing curly bracket. For the bigeometric derivative, it is assumed that all arguments and all values of f are positive numbers. This simplifies to f x equals e x f single quote x f x. Display style f caret asterisk x equals e caret x f x over f x. Closing curly bracket. For functions where the statement is meaningful, notice that the exponent in the preceding expression represents the well-known elasticity concept, which is widely used in economics. In the bigeometric calculus, the power functions are the functions having a constant derivative. Furthermore, the bigeometric derivative is scale invariant, or scale-free. i.e., it is invariant under all changes of scale or unit in function arguments and values. Multiplicative integrals. Each multiplicative derivative has an associated multiplicative integral. For example, the geometric derivative and the bigeometric derivative are inversely related to the geometric integral and the bigeometric integral, respectively. Of course, each multiplicative integral is a multiplicative operator, but some product integrals are not multiplicative operators. See product integral # basic definitions. Discrete calculus. Just as differential equations have a discrete analog in difference equations with the forward difference operator replacing the derivative, so too there is the forward ratio operator f x plus 1 f x, and recurrence relations can be formulated using this operator. See also indefinite product. Complex analysis. Multiplicative versions of derivatives and integrals from complex analysis behave quite differently from the usual operators. History. Between 1967 and 1988, Jane Grossman, Michael Grossman, and Robert Katz produced a number of publications on a subject created in 1967 by the latter two, called Non-Newtonian Calculus. The geometric calculus and the bigeometric calculus are among the infinitely many non-Newtonian calculi that are multiplicative. Infinitely many non-Newtonian calculi are not multiplicative. In 1972, Michael Grossman and Robert Katz completed their book Non-Newtonian Calculus. It includes discussions of 9 specific non-Newtonian calculi, the general theory of non-Newtonian calculus, and heuristic guides for application. Subsequently, with Jane Grossman, they wrote several other books, articles on non-Newtonian calculus, and on related matters such as weighted calculus, meta-calculus, and averages, means. On page 82 of Non-Newtonian Calculus, published in 1972, Michael Grossman and Robert Katz wrote, "However, since we have nowhere seen a discussion of even one specific non-Newtonian calculus, and since we have not found a notion that encompasses the asterisk average, we are inclined to the view that the non-Newtonian calculi have not been known and recognized heretofore, but only the mathematical community can decide that." Quote, General Theory of Non-Newtonian Calculus. This section is based on 6 sources. Construction. An outline. The construction of an arbitrary non-Newtonian calculus involves the real number system and an ordered pair asterisk of arbitrary complete ordered fields. Let R denote the set of all real numbers, and let A and B denote the respective realms of the 2 arbitrary complete ordered fields. Assume that both A and B are subsets of R. However, we are not assuming that the 2 arbitrary complete ordered fields are subfields of the real number system. Consider an arbitrary function f with arguments in A and values in B. By using the natural operations, natural orderings, and natural topologies for A and B, one can define the following and other concepts of the asterisk calculus. The asterisk limit of f at an argument A. F is asterisk continuous at A. F is asterisk continuous on a closed interval. The asterisk derivative of f at A. The asterisk average of A asterisk continuous function f on a closed interval. And the asterisk integral of A asterisk continuous function f on a closed interval. Many, if not most, asterisk calculi are markedly different from the classical calculus, but the structure of each asterisk calculus is similar to that of the classical calculus. For example, each asterisk calculus has 2 fundamental theorems showing that the asterisk derivative and the asterisk integral are inversely related, and for each asterisk calculus, there is a special class of functions having a constant asterisk derivative. Furthermore, the classical calculus is one of the infinitely many asterisk calculi, A non-Newtonian calculus is defined to be any asterisk calculus other than the classical calculus. Relationships to classical calculus. The asterisk derivative, asterisk average, and asterisk integral can be expressed in terms of their classical counterparts, and vice versa. However, as indicated in the reception section below, there are situations in which a specific non-Newtonian calculus may be more suitable than the classical calculus. Again, consider an arbitrary function f with arguments in A and values in B. Let alpha and beta be the ordered field isomorphisms from R onto A and B, respectively. Let alpha minus 1 and beta minus 1 be their respective inverses. Let D denote the classical derivative, and let D asterisk denote the asterisk derivative. Finally, for each number t such that alpha t is in the domain of f, let f t equals beta minus 1 f alpha t. Theorem 1. For each number a in A, d asterisk f a exists if and only if df alpha minus 1 a exists, and if they do exist, then d asterisk f a equals beta df alpha minus 1 a. Theorem 2. Assume f is asterisk continuous on a closed interval contained in A from R to S, where R and S are in A. Then f is classically continuous on the closed interval contained in R from alpha minus 1 R to alpha minus 1 S, and m asterisk equals beta m, where m asterisk is the asterisk average of f from R to S, and m is the classical, i.e., arithmetic, average of f from alpha minus 1 R to alpha minus 1 S. Theorem 3. Assume f is asterisk continuous on a closed interval contained in A from R to S, where R and S are in A. Then S asterisk equals beta S, where S asterisk is the asterisk integral of f from R to S, and S is the classical integral of f from alpha minus 1 R to alpha minus 1 S. Examples. Let I be the identity function on R. Let J be the function on R such that J x equals 1 x for each non-zero number x, and J 0 equals 0, and let K be the function on R such that K x equals square root x for each non-negative number x, in K x equals square root x for each negative number x. Example 1. If alpha equals I equals beta, then the asterisk calculus is the classical calculus. Example 2. If alpha equals I and beta equals exp, then the asterisk calculus is the geometric calculus. Example 3. If alpha equals exp equals beta, then the asterisk calculus is the bigeometric calculus. Example 4. If alpha equals exp and beta equals I, then the asterisk calculus is the so-called anageometric calculus. Example 5. If alpha equals I and beta equals j, then the asterisk calculus is the so-called harmonic calculus. Example 6. If alpha equals j equals beta, then the asterisk calculus is the so-called biharmonic calculus. Example 7. If alpha equals j and beta equals I, then the asterisk calculus is the so-called anharmonic calculus. Example 8. If alpha equals I and beta equals k, then the asterisk calculus is the so-called quadratic calculus. Example 9. If alpha equals k equals beta, then the asterisk calculus is the so-called biquadratic calculus. Example 10. If alpha equals k and beta equals I, then the asterisk calculus is the so-called anaquadratic calculus. Reception. The first nonlinear system of differential and integral calculus, a book about the geometric calculus, was reviewed in Mathematical Reviews in 1980 by Ralph P. Boas, Jr. He included the following assertion: it is not yet clear whether the new calculus, geometric calculus, provides enough additional insight to justify its use on a large scale. The geometric calculus, a system with a scale-free derivative, was reviewed in Mathematical Reviews in 1984 by Ralph P. Boas, Jr. He included the following assertion: it seems plausible that people who need to study functions from this point of view might well be able to formulate problems more clearly by using bigeometric calculus instead of classical calculus. Non-Newtonian Calculus, a book including detailed discussions about the geometric calculus and the bigeometric calculus, both of which are non-Newtonian calculi, was reviewed by David Pierce McAdam in the Journal of the Optical Society of America. He included the following assertion: the greatest value of these non-Newtonian calculi may prove to be their ability to yield simpler physical laws than the Newtonian calculus. Quote, Non-Newtonian Calculus, a book including detailed discussions about the geometric calculus and the bigeometric calculus, both of which are non-Newtonian calculi, was reviewed by H. Goldman, Graz, Austria, in the journal Internationale Mathematische Nachrichten. He included the following assertion: the possibilities opened up by the new non-Newtonian calculi seem to be immense. Quote, German, Die durch die neuen Kalkül erschlossenen Möglichkeiten scheinen unermesslich. Quote, Non-Newtonian Calculus, a book including detailed discussions about the geometric calculus and the bigeometric calculus, both of which are non-Newtonian calculi, was reviewed by Ivor Grattan-Guinness in Middlesex Math Notes. He included the following assertions: there is enough here, in non-Newtonian calculus, to indicate that non-Newtonian calculi have considerable potential as alternative approaches to traditional problems. This very original piece of mathematics will surely expose a number of missed opportunities in the history of the subject. Quote, Non-Newtonian calculus was used by James R. McGinnis, Claremont Graduate School and Harvey Mudd College, to create a theory of probability that is adapted to human behavior and decision-making. Seminars concerning non-Newtonian calculus and the dynamics of random fractal structures were conducted by Wojbal-Wojcinski, Case Western Reserve University, at The Ohio State University on the 22nd of April 2011, and at Cleveland State University on the 2nd of May 2012. In the abstracts for the seminars he asserted, many natural phenomena, from microscopic bacteria growth, through macroscopic turbulence, to the large-scale structure of the universe, display a fractal character. For studying the time evolution of such rough objects, the classical, smooth Newtonian calculus is not enough. Quote, a seminar concerning fractional calculus, random fractals, and non-Newtonian calculus was conducted by Wojbal-Wojcinski, Case Western Reserve University, at Case Western Reserve University on the 3rd of April 2013. In the abstract for the seminar he asserted, random fractals, a quintessentially 20th century idea, arise as natural models of various physical, biological, think your mother's favorite cauliflower dish, and economic, think Wall Street, or the horseshoe casino, phenomena, and they can be characterized in terms of the mathematical concept of fractional dimension. Surprisingly, their time evolution can be analyzed by employing a non-Newtonian calculus utilizing integration and differentiation of fractional order. Quote, the geometric calculus was used by Algamirza E. Bashir of Eastern Mediterranean University in Cyprus, together with Emin Misirli Kirpınar and Ali Pici, both of E University in Turkey, in an article on differential equations and calculus of variations. In that article, They state, "We think that multiplicative calculus can especially be useful as a mathematical tool for economics and finance. In the present paper, our aim is to bring multiplicative calculus to the attention of researchers and to demonstrate its usefulness." Quote, "The multiplicative calculus referred to here as the geometric calculus. The geometric calculus was used by Algamirza E. Bashirov, Emin Misirli, Untitled and Ali Ozyapici in an article on modeling with multiplicative differential equations. In that article they state, "In this study it becomes evident that the multiplicative calculus methodology has some advantages over additive calculus in modeling some processes in areas such as actuarial science, finance, economics, biology, demographics, etc." Quote, "The multiplicative calculus referred to here as the geometric calculus. The geometric calculus was used by Diana Andrade Philip, Babes Bolyari, University of Cluj-Napoca in Romania, and Cyril Piatekhi, Orléans University in France, to repostulate and analyze the neoclassical exogenous growth model in economics." In that article they state, "In this paper, we have tried to present how a non-Newtonian calculus could be applied to repostulate and analyze the neoclassical, solo swan, exogenous growth model in economics. In fact, one must acknowledge that it's only under the effort of Grossman and Katz, 1972, that such a non-Newtonian calculus emerged to give a natural answer to many growth phenomena. We must underscore that to discover that there was a non-Newtonian way to look to differential equations has been a great surprise for us. It opens the question to know if there are major fields of economic analysis which can be profoundly rethought in the light of this discovery." Quote, "A discussion concerning the advantages of using the geometric calculus in economic analysis is presented in an article by Diana Andrade Philip, Babes Bolyari, University of Cluj-Napoca in Romania, and Cyril Piatekhi, Orléans University in France." In that article they state, "The double-entry bookkeeping promoted by Luca Pacioli in the 15th century could be considered a strong argument in behalf of the multiplicative calculus, which can be developed from the Grossman and Katz non-Newtonian calculus concept." Quote, "The multiplicative calculus referred to here as the geometric calculus. The geometric calculus was used by Luc Florac and Hans van Assen, both of the Eindhoven University of Technology, in the study of biomedical image analysis." In their article, Multiplicative Calculus in Biomedical Image Analysis, they state, "We advocate the use of an alternative calculus in biomedical image analysis, known as multiplicative non-Newtonian calculus." The purpose of this article is to provide a condensed review of multiplicative calculus and to illustrate its potential use in biomedical image analysis. The multiplicative calculus referred to here as the geometric calculus. In Professor Florac's article, Regularization of Positive Definite Matrix Fields Based on Multiplicative Calculus, he states, "Multiplicative calculus provides a natural framework in problems involving positive images and positivity-preserving operators. In increasingly important complex imaging frameworks, such as diffusion tensor imaging, it complements standard calculus in a non-trivial way." The purpose of this article is to illustrate the basics of multiplicative calculus and its application to the regularization of positive definite matrix fields. Quote, "The multiplicative calculus referred to here as the geometric calculus. The geometric calculus and the bigeometric calculus were among the topics covered in a course on non-Newtonian calculus conducted in the summer term of 2012 by Joachim Weierkut, Laurent Hogan, and other faculty from the Mathematical Image Analysis Group of Saarland University in Germany. Among the other topics covered were applications to digital image processing, rates of return, and growth processes. A multiplicative calculus was used in the study of contour detection in images with multiplicative noise by Marco Mora, Fernando Cordova-Leap, and Rodrigo del Valle, all of Universidad Católica del Mar in Chile. In that article they state, "This work presents a new operator of non-Newtonian type which has shown to be more efficient in contour detection in images with multiplicative noise than the traditional operators. In our view, the work proposed in Grossman and Katz, 1972, stands as a foundation for its clarity of purpose." Quote, "The geometric calculus was used by Emin Misirli and Yusuf Gurf, both of University in Turkey, in their lecture, The New Numerical Algorithms for Solving Multiplicative Differential Equations." In that presentation they were stated, "While one problem can be easily expressed using one calculus, the same problem cannot be expressed as easily using another." Quote, "The bigeometric derivative was used to reformulate the Volterra products integral." Please see product integral #basic definitions. The geometric calculus and the bigeometric calculus were used by Mustafa Reza, Eastern Mediterranean University in Cyprus, together with Ali Oziapici and Emin Misirli, both of University in Turkey, in an article on differential equations and finite difference methods. A multiplicative type of calculus for complex-valued functions of a complex variable was developed and used by Ali Uza, Fatih University in Turkey. Complex multiplicative calculus was developed by Algamazari, Bashirov and Mustafa Reza, both of Eastern Mediterranean University in Cyprus. The geometric calculus was used by Algamazari, Bashirov, Eastern Mediterranean University in Cyprus, in an article on line integrals and double multiplicative integrals. The geometric calculus was used by Emin Misirli and Yusuf Gurf, both of University in Turkey, in an article on the numerical solution of multiplicative differential equations. The geometric calculus was used by James D. Engelhardt, University of Miami, and Ruo Chen Li, Shenzhen, China, in an article on pathogen counts in treated water. Weighted non-Newtonian calculus is cited by Ziyu Liu and Wensheng Guo, both of the University of Pennsylvania, in their supplement to their article, Data-Driven Adaptive Spline Smoothing. Weighted geometric calculus was used by David Bakai, Harvard University, in an article on an axiomatic foundation for intertemporal decision-making. Weighted non-Newtonian calculus is cited by P. Arun Raj Kumar and S. Selvakumar, both of the National Institute of Technology, Tiruchirappalli in India, in their article, Detection of Distributed Denial of Service Attacks Using an Ensemble of Adaptive and Hybrid Neurofuzzy Systems. Weighted non-Newtonian calculus is cited by Rizwan Effendi and Zahemi Ismail, both of University Teknologi Malaysia, together with Mustafa Matdaris, University Tun Hussein Malaysia, in their article, Improved Weight Fuzzy Time Series as Used in the Exchange Rates Forecasting of US Dollar to Ringgit Malaysia. Weighted non-Newtonian calculus is cited by Ji Zhang, Li Li, Luiying Peng, Ying Jan Sun, Ju Li, the first four from Tongji University School of Medicine in Shanghai, China, and the latter from the First Hospital of China Medical University, Shenyang, China, in their article, An Efficient Weighted Graph Strategy to Identify Differentiation-Associated Genes in Embryonic Stem Cells. Weighted non-Newtonian calculus is cited by Zheng Zhu and Li Jianzhong, both of the School of Computer Science and Technology, Harbin Institute of Technology, Harbin, China. In their article, Approximate Aggregation Algorithm for Weighted Data in Wireless Sensor Networks, the bigeometric calculus was used in an article on multiplicative differential equations by Dorota, Aniszewska, Wrocław University of Technology. The bigeometric calculus was used in an article on chaos in multiplicative dynamical systems by Dorota Aniszewska and Marek Rybachuk, both from the Wrocław University of Technology in Poland. The bigeometric calculus was used in an article on multiplicative Lorentz systems by Dorota Aniszewska and Marek Rybachuk, both from Wrocław University of Technology. The bigeometric calculus was used in an article on multiplicative dynamical systems by Dorota Aniszewska and Marek Rybachuk, both from Wrocław University of Technology. The bigeometric calculus was used in an article on fractals and material science by M. Rybachuk and P. Stoppel, both from Wrocław University of Technology. The bigeometric calculus was used in an article on fractal dimension and dimensional spaces by Marek Rybachuk, Wrocław University of Technology in Poland, Alek Ukiedziab, Medical Academy of Wrocław in Poland, and Witold Zielinski, Wrocław University of Technology. The geometric calculus and the bigeometric calculus are useful in the study of dimensional spaces. In dimensional spaces, in a similar way to physical quantities, you can multiply and divide quantities which have different dimensions, but you cannot add and subtract quantities with different dimensions. This means that the classical additive derivative is undefined because the difference f x plus delta x has no value. However, in dimensional spaces, the geometric derivative and the bigeometric derivative remain well defined. Multiplicative dynamical systems can become chaotic even when the corresponding classical additive system does not, because the additive and multiplicative derivatives become inequivalent if the variables involved also have a varying fractal dimension. The geometric calculus was used by S. L. Blyman, Lipetsk State Technical University in Russia. In an article on information technology, the bigeometric derivative was used by Fernando Cordova-Lippe, Universidad Católica del Mar in Chile. In an article on the theory of elasticity in economics, the geometric calculus was applied to functional analysis by Cengiz Turkmen and Fizi Basa, both from Fatih University in Turkey. The Mathematics Department of Eastern Mediterranean University in Cyprus has established a research group for the purpose of studying and applying multiplicative calculus. The bigeometric calculus was used by Ahmet Faruk Kakmak in his lecture at the 2011 International Conference on Applied Analysis and Algebra at Yıldız Technical University in Istanbul, Turkey. The geometric calculus was used by Gunnar Spar SV. Gunnar Spar, Lund Institute of Technology, in Sweden. In an article on computer vision, the multiplicative derivative referred to in the article is the geometric derivative. The geometric calculus was used by Ugur Kadak, Gazi University in Turkey, and Yusuf Gurf, Bozok University in Turkey, in their presentation at the 2012 Analysis and Applied Mathematics Seminar Series of Fatih University in Istanbul, Turkey. The geometric integral is useful in stochastics. See product integral # basic definitions. The geometric calculus was used by Jarno van Roosmalen, Eindhoven University of Technology in the Netherlands. In an article on statistics and data analysis, the geometric calculus is cited by Manfred Peschel and Werner Mend, both of the German Academy of Sciences Berlin, in a book on the phenomena of growth and structure building. The geometric calculus is the subject of an article by Dick Stanley in the journal Primus. The same issue of Primus contains a paper by Duff Campbell, multiplicative calculus and student projects. The geometric calculus was the subject of a seminar by Michael Coco of Lynchburg College. The geometric calculus is the subject of an article by Michael E. Spivey of the University of Puget Sound. The geometric calculus is the subject of an article by Alex B. Twist and Michael E. Spivey of the University of Puget Sound. In 2008. The article, Multiplicative Calculus and its Applications, concerning applications of the geometric calculus, was published in the Journal of Mathematical Analysis and Applications. The article was submitted by Stephen G. Krantz and written by Agamirza E. Bashirov, Emin Misirli Kirpanar, and Alyosya Peachy. The following is an excerpt from a review of that article by Gerard Leberg. What happens to the old calculus when you restrict its application to positive functions and replace the differential ratio f x plus h minus f x h display style f x plus h f x over h with the multiplicative one f x plus h f x 1 slash h display style left f x plus h over f x right caret 1 per hour text closing curly bracket closing curly bracket closing curly bracket. Answer: the usual derivative f single quote x display style f x closing curly bracket is replaced with f x equals exp lane f x single quote display style f caret star x equals left exp lane f x right single quote closing curly bracket. So you are left with some avatar of the classical calculus to unfold. The authors of this original paper do play this game. Their stated purpose is to promote this new kind of multiplicative calculus. Quote, note that f x equals exp lane f x single quote display style f caret star x equals left exp lane f x right single quote closing curly bracket should read f x equals exp lane f single quote x display style f caret star x equals exp lane circ f single quote x closing curly bracket. The article, Multiplicative Calculus and its Applications, see preceding item, was reviewed by Stefan G. Samco, University of Algarve, Portugal, in Zentralblatt Math. In this expository article, the authors developed the basics of the so-called multiplicative calculus, under which the definition of derivatives and integrals is given in terms of the operations of multiplication and division in contrast to addition and subtraction in the usual definitions. Such an approach was suggested in a book of M. Grossman and R. Katz, Non-Newtonian Calculus, Pigeon Cove, Mass. Lee Press. 1972. ZBL 0228.26002. Transforming multiplication to addition by logarithms. It is easy to see that, for instance, a multiplicative derivative equals to exp ln f single quote. The authors give also some applications where they consider the usage of the language of multiplicative calculus as more useful than the usage of the usual calculus. Quote, the geometric calculus, a system with a scale-free derivative, was reviewed in Mathematics magazine in 1984. The review was preceded by the following statement. Articles and books are selected for this section to call attention to interesting mathematical exposition that occurs outside the mainstream of the mathematics literature. The review included the following assertion. This book compares the classical and bigeometric calculi, shows their relationship, and suggests applications for which the latter might be more appropriate. Quote, the geometric calculus and the bigeometric calculus were used by Hattus Akta, Eastern Mediterranean University in Cyprus, in an article on multiplicative runge-cutter methods. Non-Newtonian Calculus, a book including detailed discussions about the geometric calculus and the bigeometric calculus, both of which are non-Newtonian calculi, is used in the 2006 report, Stern Review on the Economics of Climate Change. According to a 2012 critique of that report, called What is Wrong with Stern? Quote, by former UK Cabinet Minister Peter Lilly and economist Richard Toll. The report, Stern Review on the Economics of Climate Change, was commissioned by the UK government, and was written by a team led by Nicholas Stern, former chief economist of the World Bank. Non-Newtonian Calculus, a book including detailed discussions about the geometric calculus and the bigeometric calculus, both of which are non-Newtonian calculi, is cited by Ivor Grattan Guinness in his book The Rainbow of Mathematics, A History of the Mathematical Sciences. Non-Newtonian Calculus, a book including detailed discussions about the geometric calculus and the bigeometric calculus, both of which are non-Newtonian calculi, is used in an article on sequence spaces by Ahmet Faruk Kakmak, Yıldız Technical University in Turkey, and Fizi Basa, Fatih University in Turkey. The abstract of the article begins with the statement, as alternatives to classical calculus, Grossman and Katz, Non-Newtonian Calculus, 1972, introduced the non-Newtonian calculi consisting of the branches of geometric, anageometric, and bigeometric calculus, etc. Quote, the non-Newtonian averages of functions were used to construct a family of means of two positive numbers. Included among those means are some well-known ones such as the arithmetic mean, the geometric mean, the harmonic mean, the power means, the logarithmic mean, the eidentric mean, and the Stolarski mean. The family of means was used to yield simple proofs of some familiar inequalities. Publications about that family are cited in 6 articles. Non-Newtonian calculus was used by Z. Avazada, Z. Bagherizi, G. B. Lofmani, and F. M. Malakgarini. The first 3 from Yazd University in Iran, and the last from Islamic Azad University in Iran, to devise a numerical method for solving nonlinear Volterra integral differential equations. Application of non-Newtonian calculus to function spaces was made by Ahmet Faruk Kakmak, Yıldız Technical University in Turkey, and Fizi Basa, Fatih University in Turkey. In the lecture at the 2012 conference The Algerian-Turkish International Days on Mathematics, at University of Baji Mokhtar at Annaba, in Algeria, application of non-Newtonian calculus to continuous and bounded functions over the field of non-Newtonian geometric complex numbers was made by Zafer Kakia, Gumuşhane University, Turkey. Non-Newtonian calculus is one of the topics of discussion at the 2013 conference Algerian-Turkish International Days on Mathematics at Fatih University in Istanbul, Turkey. A seminar involving non-Newtonian calculus was conducted by Jared Burns at the University of Pittsburgh on 13 December 2012. Non-Newtonian calculus is cited in Gordon Mackay's book Comparative Meta-Mathematics. The 18 previous editions of Comparative Meta-Mathematics are entitled The True Nature of Mathematics. Non-Newtonian calculus is cited in a book on popular culture by Paul Dixon. Geometric arithmetic was used by Mutalip Ozafzar and Adam C. Sevikal, both of Yıldız Technical University in Turkey. In an article on multiplicative metric spaces and multiplicative contraction mappings, multiplicative calculus was the subject of Christopher Roller's lecture at the Singularity Summit on 13 October 2012. Singularity University's Singularity Summit is a conference on robotics, artificial intelligence, brain-computer interfacing, and other emerging technologies including genomics and regenerative medicine. Christopher Roller is a Thiel Fellow. The geometric calculus was the topic of a presentation by Ali Oziapici and Emin Misirli Kirpinar, both of the University in Turkey, at the International Isaac Congress in August 2007. Multiplicative calculus was the topic of a presentation by Ali Oziapici and Emin Misirli Kirpinar, both of the University in Turkey, at the International Congress of the Zhangjian Mathematical Society in August 2008. Knowledge of the geometric calculus. Multiplicative calculus is a requirement for the master's degree in computer engineering at Anadolu University, Malatya, Turkey. Non-Newtonian calculus was used in the article, Certain Sequence Spaces over the Non-Newtonian Complex Field, by Sabiha Tekin and Fizi Basa, both of Fatih University in Turkey. The geometric calculus is cited by Daniel Karash in his article, Hyperbolicity in Invariant Manifolds for Finite Time Processes. See also List of derivatives and integrals in alternative calculi. Indefinite product. Product integral. References. Further reading. Quotientation. An extension of the differentiation process. Robert Edouard Moritz.